Hi, and welcome to this third and last video on logistic regression, where we really connect all the dots that we've seen so far. Right, so to remind ourselves from the previous two videos in logistic regression, the idea is that we would like to predict a probability. So we would like to output a number between 0 and 1, where this number should indicate the probability of the label of a given element x being 1. Okay, and to do this, we decided on the sigmoid function in order to turn an inner product between a vector of weight w and a feature vector x into a number between 0 and 1, and it looked like this. Okay, so what we did was we tried to look at this maximum likelihood. We used this as an idea for how to derive a learning algorithm and a loss function. The basic idea was that the intention is that if I have a hypothesis w and I make this prediction, then this is supposed to equal the probability that the label is 1 given x. Which also means if I have my training data S and I have decided on a W, I can compute the likelihood of observing these labels given the model W, the hypothesis W, and the feature vectors X. And just by independence of the samples, this becomes the product for each of the individual examples of the probability of seeing that label. And what we showed before was that this is indeed the probability of seeing the given label yi if W is the model parameters and xi is the feature vector. Okay, so the idea is now that we would like to say that the solution of the model or the set of parameters W that you should choose in logistic regression is a set of parameters that maximizes the likelihood of the training data, right? So we want to find the W star that maximizes this expression down here. Okay, so when we want to do this, we had two issues. One of them is this is in the other setups, right? We're normally dealing with minimizing a loss function. Here we're maximizing an expression instead. And the second one is that this is a product over a lot of terms, whereas in the previous loss functions, for instance, for classification with the 0-1 loss and for linear regression with least squared loss, it's an average over training examples of a pointwise function. Okay, so it's a sum instead of a product. So the trick that we'll be using is the one that we saw also with the coin tosses. We'll be introducing the negative log likelihood. So what we'll do now is we'll just use this trick on this probability that we want to maximize. Instead, we're just going to minimize the negative log of this expression, right? So we take negative log of this product. Of course, the nice rule about the logarithm is that the log of a product is the sum of the logs. So we can move this product outside as a sum. So really what we're minimizing now is minus the sum of these logs of 1 over 1 plus e to the minus yi inner product between w and xi. Right, so this is the thing we like to minimize. Now, you can move this minus outside, you can move it in. If you move it in, it's the same as raising this number inside the log to the minus first, which just takes the inverse. So now it becomes log of 1 plus e to the minus yi inner product between w and xi. So this is the expression that we'd like to minimize. Minimizing this expression maximizes the expression here at the top, the likelihood of seeing the training labels. Okay, now if we wanted to look exactly like it does for linear regression and for just classification, we can always introduce a 1 over n scaling in front. Minimizing it without the constant factor and with the constant factor 1 over n is just the same problem, right? It's the same solution. So we can, of course, just minimize here the average over all the training examples of this log 1 plus e to the minus yi inner product between w and xi. Now, this here looks like something we've seen before. This looks like a pointwise loss. So we're averaging over all training examples of some function that only depends on that example, right? So this is really a loss function on a single point. So here they are, all the three different linear models and how we define the in-sample error. So for linear classification, which was the case where we used the perceptron learning algorithm, right? The in-sample error is just the average over all training examples. This indicator saying whether the prediction being the sign of the inner product is different from the label. So this is just counting the number of mistakes or just measuring the fraction of mistakes that you make. Linear regression is the average over all the training example of the squared loss. And for logistic regression, we're averaging over all training examples of this log of this 1 plus e to the minus yi inner product between w and xi. So these are the three loss function, the in-sample errors that we're really trying to minimize in the three cases. So this is what we like to minimize for logistic regression. Okay. So minimizing this in-sample error for logistic regression really maximizes the likelihood of seeing the training data labels. This is the intuition for what's going on if we minimize this expression. This is the motivation for choosing this loss function. Okay, so this is our loss, and let's try to just look at it a little bit just to see that this is a sensible loss function. So let's try to just parse what's happening in this expression. So let's try to look at one of these single terms, one of these contributions to the loss for a fixed element I. So we can see here that up in the exponent, right, we have the inner product between W and Xi. And what we see is that if this inner product has the same sign as the label, then this exponent here is negative, right? Because yi times the inner product becomes a positive number and you negate it. So the exponent becomes negative, and this means that the loss goes down. The loss is small. And we take log of it's an increasing function of this term here. So the loss is really going to be small if this inner product has the same sign as yi. Again, we can think of it if we think back to the case of just the classification problem, right? The sign of this inner product is the same as yi if they're on the right side of the hyperplane. Xi, yi is on will be predicted correct by this hyperplane. So the intuition is also in this case that if they have the same sign, then as this inner product grows, the whole loss becomes smaller. So which means you become more correct, and which means intuitively that you move further and further away from the hyperplane on the right side of the hyperplane. So you become more and more correct and more certain in some sense in the prediction. On the other hand, right, if this inner product has the opposite sign of yi, then the exponent here is positive, and then the loss is growing, right? With the if you have a larger and larger inner product here, meaning that you're further and further away on the wrong side of the hyperplane, then you pay a bigger and bigger penalty in the loss, right? So you kind of, unlike the classification case where we just count mistake or not, are you on the wrong or the right side of the hyperplane? Here we're really saying the further away you are on the correct side, the better, and the further away you are on the wrong side, the worse it is. So this is some intuition for what's happening in this loss function. Okay, so this is our loss function, and we'd like to minimize it, right? We'd like to minimize this in-sample error. Okay, so what we've been using, of course, the whole reason for talking about convex functions in the previous video is that this in-sample error is actually a convex function of W. And we'll not prove it here, but this is a rather simple exercise to show that this in-sample error is in fact a convex function. Okay. So it's a convex function, so we already know a good strategy for minimizing such a loss function, right? We should just compute the gradient and set it to 0. Right? We already know there's only one minimum, and it's obtained by setting the gradient to 0, and there are no local maxima and no saddle points, right? So all we have to do is compute the gradient vector and set it to 0, and then we've solved it optimally. Okay, and this is just by convexity, this will be the optimal solution. Okay. So let's just try and start by computing this gradient vector, right? So recall again, like the gradient vector in each of the j entries, it contains the partial derivative of the in-sample error with respect to wj, right? That's the jth entry of the gradient vector. Okay, so we have to compute the partial derivative of this expression with respect to wj. And the first step that we do when we have a sum like this is that we observe that the partial derivative of a sum is just the sum of partial derivatives. So we can, and also the constant factor just stays outside. So we can move the derivative inside, right? So we need to compute the partial derivative with respect to wj of this expression log of 1 plus e to the minus yi in a product between w and xi. So this is what we have to compute derivatives of. Okay, this is again is a composite function. So we'll be using the chain rule, which has been used a couple of times by now. So the chain rule tells us to look at the outer function, right? The outer function is log x. The derivative of that is 1 over x. So we have to take the derivative, which is 1 over x, and the x should be the inner function, right? So we have 1 over the inner function here. So we just take 1 over the inner function, and then we need to multiply with the partial derivative of the inner function, right? So we still have to compute this partial derivative up here for the inner function. This is just an invocation of the chain rule here. Okay. So let's proceed to compute this expression here. And so basically we can get rid of the 1 plus, right? So because the 1 is an additive constant, it just goes away. So this partial derivative is just the partial derivative of the latter expression here. Okay. This time here, again, have a composite function where the outer function is e to the x and the inner function is minus yi w transpose xi. So we know that the partial derivative of e to the x is just e to the x. So we get a term that is just e to the inner function, which is just the same as we had before. And then we need to multiply with the partial derivative of the inner function. Right, so we still have to compute the partial derivative of this minus yi w's inner product with xi with respect to wj. So far, it's just all using the chain rule. Now, again, if we unfolded this inner product here, right, it's a sum over all the coordinates of w. So we take the jth coordinate of w and multiply with the jth coordinate of xi, which means that the only term that contains wj is the term minus yi wj xij, which means that if we take the partial derivative with respect to wj, we only get the coefficient on wj, which is minus yi xij. So, here I just moved it up, and so it's the same expression as before. And if we take this partial derivative, as I mentioned, you get minus yi xij, because that's the coefficient on wj in this inner product up here. So this is the full gradient vector, or the jth entry of the gradient vector, sorry. So it looks like this. And so let's just write it as a vector instead, right? Because this is the jth entry of it. We can see what depends on j. It's only here xij. So really, you have this whole factor here that you multiply onto xij. All of this is a factor, everything in front, that you multiply onto xij. And the factor does not depend on j. So the full gradient vector is really, you take this whole factor and you just multiply it onto xi. Right? So you take all this entire factor in here and multiply it onto xi. So this is the gradient vector, really. So the only thing that's a vector here at the end of it, you have the xi here, it's a vector. Yi is a number. This inner product is a number. This is a number. So everything else is a number. Okay, so this is the gradient vector. Okay. The gradient vector is here. Let's just try to see if we can simplify it a little bit by recalling this sigmoid or logistic function that we already introduced. So the sigmoid function again, right, is this expression here, right? 1 over 1 plus e to the minus z, or which is also the same as e to the z, or 1 plus e to the z. So let's just see if we can use this to simplify the expression up here, right? What we notice is that basically this e to the minus yi w transpose xi is basically corresponds to this e to the z term, and down here you have the 1 plus e to the z. So what we can see is that this whole expression here is really just the sigmoid function on minus yi w's inner product with xi. And so this whole expression is multiplied onto minus yi xi. So we just move the minus in. So this is the gradient vector. It's a much simpler expression for it, right? You just average over all the training examples. You take minus yi, you take the vector xi, and then you multiply it with the sigmoid function applied to minus yi inner product between w and xi. So that's the gradient. Great. So, our approach was we have a strategy to minimize the ensemble error. We just have to compute the gradient vector and set it to 0. And we just found out that this is an expression for the gradient vector. So all that remains now is just to take this expression and set it to 0. Right, this is also what we did for linear regression. We computed the gradient and we set it to 0. Now, if you stare at this for a while and you try to set this expression to 0, I think you'll quickly realize that this is a hard task. You know, how do you figure out what is the choice of w that makes all of this 0, right? The problem is that this does not really have an analytic solution or a closed form expression, right? So this really is really a problem, right? Because we cannot really complete this program we set out to do, right, by computing the gradient and setting to 0, because there's not really a closed form expression for this final solution. So that's the problem, right? So what do we do now? Has this all been for nothing, that we've looked at the gradient and we have argued that the function is convex and so on, right? Because we can't actually do the last step, right? So we cannot analytically set this gradient to 0. So then how can we instead try to minimize this ensemble error if we cannot set the gradient to 0, right? What other strategies do we have available? And can we still use this convexity for something, right? Was there still a reason why we went through all this trouble of defining convex functions and trying to argue that at least this ensemble error here for logistic regression is a convex function? This is still useful for something. And what we'll see here, the technique for actually trying to address this is what's called gradient descent. Okay, so let's try to spend the next few slides on introducing gradient descent and the ideas behind it. Okay, so as a side step, let's try to again look at problems of just minimizing a function of a single variable, right? So out here on the x-axis, you have the value of the variable. On the y-axis, you have the evaluation of the function. Let's say we would like to minimize this function, right? So intuitively, we'd like to find this minimum here. So the basic idea in gradient descent is to imagine that this is a landscape and you have a ball that's rolling downhill, right? So basically you have these balls that are sitting somewhere in the landscape, and then, if it's a ball, it'll roll downhill and finally it'll settle in these minima, right? That's the basic idea. The basic idea is if I put a ball on the surface and let it roll downhill, it will end up in a local minimum. Okay. So how can we use this to try and minimize a function, right? So the basic idea is that we'll just try to simulate this rolling of balls downhill so that they will move towards these minimum. Okay. So how can we then simulate the rolling of a ball? Right. So what we do is initially we just say, okay, I just start somewhere, right? So I put my W in some place, maybe a random place, or maybe you somehow know something about your function that makes you start in a good place. But anyways, let's just start somewhere. So let's say we could, for instance, start out here. And now we want to find out which direction we should move to go downhill, right? Should we move forward in W or should we decrease W to go downhill? Of course, the answer is that we should decrease W, but how can we in general determine this just based on the function L? Right. So what is the downhill direction? One approach for finding the downhill direction is to compute the gradient of the function at this W. In general, just to compute the derivative or the slope of the tangent, right? So for one variable, the gradient is just the slope of this tangent here. So down here, you can see, right, the slope is negative, and up here, the slope is positive. So what you can see here on the right-hand side, right, the slope is positive, then the function really, what it means is that the function is an increasing function at this W. So what you should do to roll downhill is to roll backwards, right? Similarly over here, right, if it's negative, then the function is decreasing in this position. So what we should do is we should roll forwards, right? We should increase W in order to go downhill. So that's the basic idea in gradient descent, right? So we start by computing the gradient at W. Then we're going to take a step in the opposite direction of the gradient, right? If the gradient is positive, we're going to go backwards. If the gradient is negative, we're going to go forwards. And the way we can do this is that we imagine that there's a step size, which we call eta. And then what we do is we just take our current W and then we update it by subtracting the step size. So think of it as a small constant times the gradient. So if you're over here, right, in this left position, what we'll do first is we'll compute the gradient. The gradient is a negative number. And we'll multiply this negative number with a small constant, small positive constant. So it's still a negative number. We subtract off the negative number from W, meaning that we add a positive number, right? So we go forward. Then we repeat again, right? That's the idea that, okay, now we've hopefully gone closer to the minimum. So now we compute the gradient again. And then we're going to see here, again, it's negative. So we take a small step in this direction. So we move a little bit forward. Right? So perhaps we overshoot the minimum as we did here. But now the idea is that the gradient here now becomes positive. So if we compute the gradient here, we have a positive number, multiply with a small step size. So we still have a positive number that we subtract off from W, which means that now we're going to go backwards again. So we're going to move closer and closer to this minimum. And a second observation is that, well, we know that the gradient is exactly 0 at the minimum, right? And the intuition is that intuitively, as you get closer and closer to this minimum, the gradient also becomes closer and closer to 0, which means that these steps that you're taking become smaller and smaller, right? So you kind of just finally you're settling near this minimum, right? You're moving in tiny, tiny steps towards the end, so you don't really roll out of this hole that you found. Right, so there are a couple of observations, right? There's this step size that one needs to choose, and observation kind of if you choose a step size too large, then the idea is that then you really overshoot this minimum, right? Because you're taking a huge step in the opposite direction of the gradient. So maybe you start here at this hill, you have a huge step size, maybe you walk all the way over here on the right. Whereas if your step size is really small, you're taking tiny steps each time, so maybe it's going to take you a very long time to get to the minimum. Okay, so here's just a picture. Let me try to explain what you can see in this picture of the effect of using different step sizes. So what you see here is a plot of a function that depends on two variables, and the color intensity shows the value of the function. So dark blue means it has a low value, meaning that we go towards the minimum, and this little square in the middle is the actual minimum of the function of two variables. The red one here means that we have high values, so we're not at the minimum. And so basically the idea is that we start somewhere. So that's the idea here. Out on the far right, we have different starting positions. So you start your ball in some position, and then you take little steps by computing the gradient and taking a step in the negative direction of the gradient. So each of these jagged lines that you see here is what happens in each of the steps of the algorithm. So you can see over here on the far right that if we have a very large step size, and something that could happen is that we kind of, when we get close to the minimum, then we still take these giant steps up and down without settling in on the minimum. If you set the step size about right, then we take these small steps and we pretty quickly get to the center of this figure where we have the minimum of the function. Finally, here on the left, if we have a really small step size, then we just take tiny steps here on the function, and we don't really get to the minimum fast enough because we're just taking tiny steps all the time. Okay. Now, if we go back to this picture of minimizing a function of a single variable, then the previous picture had multiple minima. But the observation is that with convex functions, there's only one minimum, right? And there's no saddle points and no local maxima, which means that basically you're always in this hole that contains the global minimum at the bottom. So, which means that the direction that you step into is always towards the minimum. You might still overshoot it, but you're really always walking towards the minimum of the function if it's a convex function. And you can generalize this to multiple variables instead. So for multiple variables, there's an analogy to the single variable case where in the single variable case, right, the value of the gradient is just the slope of this tangent. Now, if you go to multiple variables, then if you look at the gradient vector, so now it's not just a number, but a vector, if you take a step in the negative direction of the gradient, okay, so you take minus the gradient vector, then you can argue that this is actually a step in the direction of steepest descent from where you are, right? So you should imagine that your function is now a landscape, at least for two variables, it's a landscape. And then the gradient points in the direction where it goes the fastest uphill, and the negative gradient points in the direction where it goes the fastest downhill. So really what you're doing in gradient descent, when you have multiple variables, is that you want to walk downhill as fast as possible. And the way you do it is that you start in some W, and in each step, you compute the gradient vector at the current W. You take this gradient vector, you multiply it with a small step size, and now you take this step in the negative direction of the gradient. Right? So you're walking downhill as fast as you can with this given step size. Okay. The step size here is often also in learning algorithms referred to as the learning rate. So how fast should you update your current model or hypothesis? And now what we get to, and here's just the vanilla gradient descent with a fixed learning rate. So this is an algorithm for minimizing a function of multiple variables. What you do is you minimize or you initialize your vector parameters W, and you just say, while you have more time to optimize, what you do is that in each step, you compute the gradient of the loss function at the current position. You multiply it with a step size, and you subtract it off from the current set of parameters. So you're just walking downhill in the direction of steepest descent until you're out of time, and this is what you return. So of course, one should argue, how should you choose this step size in practice? And it turns out, at least for this fixed learning rate gradient descent, it often works well if the step size is about 0.1. And this is just a practical rule of thumb that this is a good choice of learning rate. Okay. Let me just add that there are versions of gradient descent where the step size is not fixed and you try to choose it in a clever way. But for these videos, let's just assume that there's a fixed learning rate. Okay. So now I guess we're ready to go back to logistic regression. So now let's try to apply this framework of gradient descent for logistic regression. So what the framework tells us is that, well, we should initialize our parameters somehow. And, maybe you could choose them randomly as normal distributed entries or what have you, right? That's a reasonable choice. So initialize your parameters. And then the algorithm is just saying, while you have more time, you would like to compute the gradient of the in-sample error at the current W, right? So even though we couldn't analytically set this gradient to 0, we computed an expression for the gradient. The gradient had this expression here. And with the current choice of parameters W, we can evaluate this expression, right? So this just gives us a vector. Recall that each of these xi's is a vector, and then you have some scaling on each of the vectors. So the gradient is really just a vector here that we can compute for any current value of W. We can compute what is this gradient. And then all we do is we just update the current parameters by taking a small step in the negative direction of the gradient, right? So the eta is the step size, and you subtract off the gradient times eta. Once you're out of time or you're satisfied with the W that you obtained, you just return the W. So that is gradient descent for logistic regression. And since the logistic regression loss function is convex, this is going to move towards the global minimum, right? So if we examine this algorithm, maybe it's interesting to know how fast does it run, right? So evaluating this whole expression, right, there's a linear number of terms in it, right? There's a linear number of data points. Actually, maybe the running times is at least linear, and maybe it's even worse if you include the d features on these vectors, right? So then I guess it's nd time even. So linear time to do one step in this algorithm, and right. So it's a linear time algorithm for every step, and so the running time becomes the number of steps you need to take times n, right? So that's the final runtime. Okay. And now, as I mentioned before, right, the logistic regression loss function is convex, so this is actually going to move towards the global minimum. Okay, so it's a good algorithm. It will move towards the global minimum, and of course, you have to set this learning rate right. And a good rule of thumb is to choose it, so it's maybe something like 0.1. Okay. So one issue with gradient descent, and let me just introduce some twist to it, is that it takes linear time to compute the gradient. And if we're doing many steps, maybe we're doing millions of steps or at least thousands of steps, then we have to scan through the whole training data set thousands of times, right? So this can actually be super expensive in practice. In particular, it may be too expensive compared to how fast you make progress on getting a good W. And so for that reason, right, there's another version of gradient descent that I'll just also introduce here. And this is called stochastic gradient descent. So it's just a twist to the previous one. So it has the same kind of initialization of the vector parameters W, and then it has the same loop that you say, oh, while I have more time, I'm going to try and minimize my function. So the basic idea now, instead of computing the gradient on the whole data set, that's what we did before, what we'll do instead is that we're going to just say, okay, I'm just going to pick one training example randomly from my n training examples. And then I'm going to pretend really that this is my only training point. If this was my only training point, then at least if I go back to the previous slide, right, here in the gradient vector, I'm averaging over all the training examples of this expression. But if I only had one example, I don't need to average, right? There's only one point, x comma y. So the gradient now is going to be minus y times x times the sigmoid function and minus y, the inner product between w and x. So now this is a much faster thing to compute, right? This is a constant time. It only involves a single data element. It's O of d time if you include the time to look at the features. Okay. And then you just take a small step in the negative direction of the gradient. So it's the same kind of algorithm, but you're cheating a little bit, right? You're not looking at you're actually not minimizing the original loss function. You're just kind of pretending that there's only a single data point. And each step of this algorithm now takes constant time, so it's much faster. But the downside is, right, you're kind of saying that I only zoomed in on one of these terms in the sum, right? I picked one of them at random. And then really what I'm saying is I'm minimizing that term, right? I'm taking a negative step in the direction of the gradient if that was the only term in my loss function. So one of them makes progress, but many of the other terms in the sum might become bigger. In fact, the whole sum might grow if you do this. Okay. So is there any reason why this would be a good idea? And maybe one hint at why the stochastic gradient descent makes sense is that actually this gradient vector that you have here, it's actually going to be correct in expectation. And so what do I mean by that? So if I look at the expectation of this gradient, so this whole expression for the gradient, right? What is the expectation, right? The expectation is the sum over all the outcomes of these random variables x and y of the probability of that outcome times the outcome. right? So the n possible outcomes, right? It's uniform random between x1, y1 to xn, yn. So basically, you're going to sum all the n outcomes, weigh all of them by the probability that you get that outcome, and then you get what is the outcome if I pick the sample xi, yi. So this is really the expectation, is just the average over all the training examples of minus yi, xi, sigmoid function and minus yi in a product between w and xi. And this is exactly equal to the original gradient. Okay, so in some sense, the intuition or motivation for doing stochastic gradient descent is that even though you're not guaranteeing that you're walking in the right direction, you're not necessarily minimizing the in-sample error, the direction, or the expectation of the direction that you're stepping in is actually equal to the gradient. Maybe one thing here, if you're not so comfortable with this whole thing inside the expectation, is a vector. So the expectation of a vector is just the vector where each entry is the expectation of that entry. Okay, so that's just the definition here. Okay. So what you do in practice is actually none of the two. Right, so we had gradient descent, which you actually walk in the correct direction every time, but the problem was that it's slow to compute the gradient. And for stochastic gradient descent, you sample just a single point and walk in that direction. It has the right expected gradient, but and it's very fast, but the problem is that you're not guaranteed to walk in the right direction. Let me just finish by showing you what you actually do in practice. What you do in practice is what's called mini-batch stochastic gradient descent. So what does it do? So here's the final algorithm. So it looks like before, you still initialize W, you still have these loops while you have more time. And what you do is, instead of sampling 1 point from your training data, you're going to sample B points. Okay, so B is a parameter that you choose. You're going to sample B points uniformly from the training data. And then what you're going to do is basically you're just going to pretend that I only had these B samples. Okay, which means that then the gradient would be the average over these B examples of the gradient for that concrete example here. Right, so you would get the average over B examples minus, you take each of the ith of the samples, you take the yi, you take the xi, and you take the sigmoid on minus yi in a product between w and xi. So you compute the gradient averaged over these B samples that you drew, and then you're going to take a small step in the negative direction of the gradient. It's exactly similar to this stochastic gradient descent. You can still show that in expectation, this is the right gradient. And this holds both if you do these samples as independent sample with replacement or without replacement, meaning that either you can sample the same training point multiple times or you cannot sample it multiple times. It actually has the right expectation in both cases. Also, or the basic idea of this, by including more points, is in some sense you have less variance in this gradient that you compute, which means that it's going to be more strongly concentrated around the true direction of the gradient. Okay, so that's the intuition here for including more points, is that then you're more certain that the direction that you step into is actually close to the true direction of the gradient if you had evaluated it on all n training examples. So what you do in practice is you just have to choose this B, and what's something that seems to work well, and as a general rule of thumb in practice, is B is something maybe between 4 and 64, right? So you just include some few data points, more than a single one, and then you use this to sample. Okay. So maybe one last notice here, because this is actually still not the final algorithm that you use in practice. The observation or the problem with this algorithm that we have here is that if I have a really large data set and all this data is stored in maybe a huge matrix or something, then if I'm sampling B elements, it's because of the way the memory hierarchy in a computer works, it can actually be rather slow to access B random elements, right? Because you're doing random accesses in different locations of a matrix. So this is just slow if you do it in practice. So what you do instead is you're going to shuffle all your n training examples, do a random permutation of them, and then you're going to group them into batches of B elements. Okay, so let's see the final algorithm here. So you have all your n training examples, and then you permute them randomly. Okay, so now they're in a random shuffled order. And then you loop over the data in batches of B elements, right? So there's n over B batches. And each batch, you just kind of take the next B data items that you have, and then you use those to do one step of gradient descent, right? So you compute the average of all these B examples of the gradient, And then you're going to take a small step in the negative direction of the gradient, right? So this is just kind of, you're really using all the data, but you're using it in these batches of B. And you're just kind of in each of these batches, you're kind of pretending this is the only data that I had. So I'm kind of minimizing the loss function just on those B and data items. That's the basic intuition. Okay. Now, of course, also, I guess an advantage of this version compared to the one where you randomly sample B elements is that once you're done with scanning through the permutation, you're guaranteed to have looked at every training example exactly once. Whereas if you sample B elements, you take a small step and you sample B new elements, there might be some that you see way more times than others. Okay, so this has a kind of like an effect of making sure that you see each training example equally often. Okay, so that's another motivation for using this. Okay, now there's some common terminology used for each time you make such a permutation. This is typically called an epoch in training. This is a training epoch is when you permute the data and scan through all of them in batches of B. That's one epoch. And in practice, it often happens that, it seems to be a good rule of thumb that when you start training your machine learning model in the beginning, you should have a reasonably large step size so you quickly make progress. But as you've trained for a while, the model it should be getting closer and closer to something optimal. And oftentimes it's a good idea to say that every now and then, once I've completed a fixed number of epochs, maybe 10 or something, I reduce this step size a little bit. Okay, so I kind of take smaller and smaller steps for when I've been training for a long time. Okay, this is just a practical improvement. Okay, so this is just stochastic gradient descent, and it actually works with any pointwise loss function that's differentiable. Right, so it doesn't only work to logistic regression, it's a general framework for minimizing pointwise loss functions, right? Because all we're really doing here is we have some parameters W, and then we permute the data and scan over the data in batches of B. So we take B elements, and then basically we're taking this in-sample error as if we only had those B elements, right? So we're taking those B elements, pretending those are the only ones. And if those were the only ones, we compute the gradient of this loss function summed over those B elements, or averaged over those B elements. And then we take a small step in the negative direction of the gradient. And this is just a general template, right? If you have an arbitrary loss function that's differentiable, you can plug this in, right? So for instance, you could do this also for linear regression, right? We actually don't have to compute the analytic solution and set it to 0. You could actually use the loss function for linear regression here, the least squared loss, and you'll still get an algorithm that you could run based on gradient descent. Okay, so gradient descent is really a powerful framework that really works as long as you have a pointwise loss function that's differentiable. Then you can apply mini-batch stochastic gradient descent. Okay, and so mini-batch stochastic gradient descent is really, I guess, the most important algorithm in machine learning. Right, it's used everywhere inside all of these libraries for machine learning, right? So the TensorFlow, the PyTorch library, and you've also worked with the scikit-learn library and Keras. So it's just used everywhere, and this is the kind of the engine of all in particular for deep learning optimization of machine learning. But it's just used all over the place. So let me just try to summarize what we saw in these 3 videos on logistic regression, right? So we had a hypothesis W, which is again supposed to be a linear model. And the way we decided to make predictions is that we're going to apply the sigmoid function to the inner product between W and X. Sigmoid function is just defined like this. And the intention that we want is that the output here should be an estimate of the probability that the label Y is 1 given this feature vector X. Then we defined, if we actually assumed that this was the case for a given W, then we could define the likelihood of seeing the data labels for this W, which is just by independence, the product over all the examples of the chance of seeing each of the individual examples. So we wanted to maximize this likelihood, and then we used this trick of taking negative log. So we're saying that maximizing this likelihood is the same as minimizing the negative log likelihood. And then we showed this negative log likelihood is a convex function. We computed the gradient of it, and then we used gradient descent to minimize it, simply because there was no analytic solution for setting this gradient to 0. Right? So if you run this logistic regression, you're going to get models that look like this, where if I have 2 classes of data here, these are the labels assigned to the training points. If you run logistic regression in this data set, We find a hyperplane that's basically here at the middle of the white area. And the prediction, if you ask for a given point, what is its label, it's going to output a number between 0 and 1, right? 1 meaning I'm very certain that the label is 1. And if I output 0, I mean I'm very certain that the label is -1. And you can basically see the coloring here means that the further away you move from the hyperplane on the top here, the more certain you are that the class is blue. That's the class 1. And below it, you're more certain that the class is red, the -1 class. Okay, and basically here, the points that are very close to the decision boundary, you're basically going to say almost 50-50 on which class they are, which makes sense, as you can also see in this data plot, right? There are both types of points here nearby the decision boundary. And so that's all for logistic regression.